We're here with LSU's Petroleum Engineering Reservoir Dynamics 4050, and today we're here to talk about the relative permeability changes via polymer injection in maturing reservoirs. There are multiple advantages of a polymer injection in a water-drive reservoir. The first of which is companies have the economic incentives to limit the amount of water produced compared to oil because of disposal cost. The second of which is an advantage of pressure mitigation of the oil to the reservoir instead of water, so essentially we have an efficiency of pressure. The third of which is a management of water influx into the wellbore. And due to the previous three advantages, we experience a decreased relative water permeability compared to the oil relative permeability.
There are three scenarios where we would want to employ polymer injection. The first is production well water shutoff. The second is mobility control injection to increase viscosity of a water flood. The third is injection well reprofiling to redirect water floods to low perm oil zones. Each of these scenarios would recondition relative water permeability.
The biggest strength of polymer injection is that it effectively reduces the permeability that is available to formation water by increasing its viscosity. With the viscosity being increased, the water is unable to move through the passages that it was previously traveling. As a result, this acts as a lowered permeability. Oil, on the other hand, is not affected by the polymer gel and is able to flow freely through the polymer-filled channels to the wellbore. This effect is shown in Figure 1 as the gel is essentially acting as a screen that only oil can pass through. Although polymer flooding has been conducted since the early 1980s, a new technique is being developed to exploit the advantages of polymer gels. Some operators are now pumping polymer gel directly into individual production wells, into homogeneous formations with naturally high permeability. These are typically dolomites and sandstones. The wells selected are mature and tend to be fully pumped down, having very low cuts of oil and high cuts of water. The goal is to reduce the channels available to water, i.e. reduce permeability, while retaining oil permeability. So how does this change of permeability actually affect flow? Essentially, we are changing the effective wellbore radius of water, or rather, we are altering the area that the pressure drops affects, thus causing an increased flow of oil and a decreased flow of water. Before we discuss how these changes work, we must first look at a few requirements and assumptions. It is assumed that perforations are set moderately high in the formation to prevent the early onset of the well watering out. A homogeneous matrix is also required, meaning that the entire formation has relatively the same permeability, with no fracture-sized channels, which is one of the major differences from other type of polymer jobs. Oftentimes, however, permeability in the vertical direction is greater than the permeability in the horizontal direction, which contributes to why water is able to travel so easily up to the wellbore. Adding to the problem is that most of these formations are very thick crude and is far more viscous than the formation water. The combination of these issues lead to water being far easier to produce. Now we are ready to discuss how the permeability changes the effective wellbore radius. When injected, the polymer gel flows down into the open channels filled with water and essentially acts as a screen, holding the water back. This function of the polymer allows it to act as a skin only affecting water. As the polymer gel decreases the permeability available to water, a positive skin factor is attained from the skin factor equation shown. This positive skin factor for water results in a decreased effective wellbore radius for water production from the effective wellbore radius equation. This, however, is a good result as the polymer skin does not affect the flow of oil, meaning oil will be able to travel to the wellbore freely without the impediment of water. Another way of showing the changes of flow due to polymer is by looking at Darcy's flow equation. We can see that for oil, all values will be standard to the formation with a skin factor of 0. Values in regard to water, however, will yield lower permeability, higher viscosity, and a positive skin factor due to the polymer injection. The flow rate of water will be significantly less after the polymer treatment. Now that the oil does to compete with water to the wellbore, more oil will be produced.
J.L. White suggests that there is a disproportionate permeability reduction when introducing a polymer to oil and water, caused by oil and water following independent paths. From the figure, you can see during high water fractional flow, water flows through the easiest most accessible pathways, while some pathways contain oil and are inaccessible to water. If the polymer is a water-based gel, it will follow the pathways that are available to water, leaving the oil-connected pore space unaffected after polymer treatment. Because of this, water-based polymers reduce water permeability more than oil permeability. The mobility ratio is mathematically defined as the ratio of the mobility of the displacing fluid to the mobility of the fluid being displaced. In a conventional water flooding technique, the displacing fluid is water and the fluid being displaced is oil. For example, if the mobility ratio were equal to 5, that would mean the ability of water to flow is 5 times greater than that of oil. Therefore, a mobility ratio less than or equal to 1 would be ideal. Little can be done to improve flow characteristics of oil in the reservoir other than thermal recovery methods, so polymer flooding is used. For polymer flooding, polymers are added to the water in order to increase the viscosity of water and decrease the effective permeability to water, reducing the mobility ratio. This takes place with partially hydrolyzed polyacrylamides and xanthan gum polymers, and the reduction of the permeability of the formation to water remains reasonably permanent, while the permeability of the formation to oil remains somewhat unchanged.
One context of polymer solution injection is the reprofiling of water flood injection wells. Reprofiling becomes an option when reservoir heterogeneity leads to water channeling frequently caused by natural fracturing systems that create high perm thief zones for injected water to make early entrance into oil zones. Reservoir heterogeneity can be an ambiguous term, but here it needs to be clear heterogeneity pertains to flow irregularities and dynamic conditions of the porous media. These high perm channels decrease water flood efficiency, leaving oil behind. Water takes the path of least resistance as shown in the figure. The right figure illustrates how fractures make high velocity concentrations for flow, whereas the left figure shows more uniform patterns spread across a larger area. When polymer reprofiling is selected as a solution for high water production, the goal is not to displace oil in lower perm regions, but the goal is to send polymer to high perm water flows. Polymer solutions then leave an absorbed layer on pore walls, which is relatively permanent and thickness is in the order of magnitude of the pore size. To the right is a relative perm curve that depicts the relative perms for wetting and non-wetting phases before and after injection of a core with a 1 gram per liter polysaccharide G solution. The solid lines represent relative perms at various water saturations before injection. The dashed lines represent after injection. As you can see, the relative perm for oil is practically constant. However, the relative perm for water is cut in half. A microscopic viewpoint helps clarify the reasons for the relative permeability phenomena occurring in the previous slide's figure. Polymer molecules are hydrophilic, only filling volume occupied by water on the outer edges of pores, as depicted in this slide's figure. These molecules can flex to some degree, allowing loops and tails to form. Pore geometry is typically irregular in real rock, and pore walls may form sharp angles and corners, allowing molecule tails to bridge, further reducing the relative water perm. In water-wet sandstones, the oil phase tends to flow in the center of the pore cross-section. An absorbed polymer layer would reduce the size of this cross-section, therefore decreasing relative water perm. However, the increase in water weldability of the rock, which creates less friction for oil phase to flow, competes with the reduced cross-section to result in an overall little effect on relative oil perm by the absorbed polymer layer.
My name is Taylor Frick.
And I'm Jake Gearman.
We're here with LSU Petroleum Engineering Reservoir Dynamics. We've set up a simple experiment to show that a polymer saturated sand will have a decreased relative water perm as compared to a sand that is not saturated with a polymer.
In order to show this important reservoir dynamics property, we've designed a simple experiment. It has a 2-foot, 2-inch inner diameter PVC pipe with a filter on the bottom that allows water to flow through freely but contains the sand in the apparatus. The experiment will consist of two parts. The first part will be the regular unconsolidated sand. We fill the sand up to the already pre-measured mark in the apparatus, and we will flow through water through the experimental apparatus. One of the parameters we must keep constant during this experiment is the pressure. In order to keep this pressure constant, we will keep a constant hydrostatic head at the top by adding water as needed through the experiment. The first part will consist of 3 5-minute trials with the unconsolidated sand. After we get a steady flow rate of water going through the experimental apparatus, we will then replace this bucket with a measurable device for 5 minutes. After 5 minutes, we will measure the amount of water that has flown through, and from this we can derive our flow rate. We will repeat this 3 times for the unconsolidated sand to get accurate data. The second part of the experiment will consist of mixing a polymer solution with the sand, filling it back up in the experimental apparatus to the pre-measured mark, and repeating 3 more trials for 5 minutes to see how our flow rates compare of the unconsolidated sand in the first part of the experiment with a polymer solution saturated sand in the second part of the experiment.
For our experimental data and results, we first derived an equation for permeability in Darcy units. Secondly, we used a constant viscosity of 1 centipoise, a length of 1 foot, which equals 30.48 centimeters, and an area of 20.268 square centimeters. For flow rate, we used milliliters collected from our volume per second, which equates to centimeters cubed per second, which we plug back into our equation. For delta P, we equated our rho GH to 0.034415 atmospheres. We plug this all back in to find our relative permeability and our flow rates. For the first part of our experiment, we showed a 66.517 Darcy permeability. For our second part of our experiment, we showed a 30.83 Darcy permeability. This equates to a 53.65% reduction in flow rates and permeability between our first part of our experiment with regular sand and our second part with polymer solution.